Alright, in the previous video 3.3, we discussed about the basic incremental conductance method, right, and its implementation in a digital environment. In this video, we are going to look at two variations of the, or rather than two derived versions of the incremental conductance methods, which are more suitable for analog implementation, which can be implemented in analog circuits also. These versions can also be implemented in digital circuits, certainly. So let's start with the first method, wherein we have we are defining a term E, which can be used as a short form for error, and let us define E is equal to I by V plus di by dV, right? As we have seen in the previous video, that if this is P versus V graph, then we have shown that if this term E is greater than 0, that means I am on the left hand side. If E is equal to 0, implies we are operating at MPP, and if this E is less than 0, we are operating in the right hand side, where this point is MPP and corresponding RHS and LHS are defined. So one way of realizing this is, our ultimate aim is to generate V reference, right? VPV reference. Now using this input, how do we generate this VPV reference? First of all, if you are doing an analog implementation, then what we need to do is we need to start with the current and the voltage measurement and generate this term E, right? So for instance, you can do, if you want di by dV, first thing you can do is you can create a derivative circuit, and you can find di by dt. Similarly, you can find dV by dt, right? And then use a circuit where you divide one term from the other so as to find, the other way around, you divide the bottom term from the top term to find di by dV. Right? Similarly, we can take this sample I and this sample V, and we divide them directly to get the term I by V, and then we can add both of these signals to get the final term, which is E. Now let's say this E, what is the value I want for this E? Ideally, I would like this E to settle at 0. So let me compare it with 0 and pass it through a controller, which could be a proportional integral controller, and generate VPV reference, right? So I'm just comparing it with the 0 and then passing through a PI controller to generate a VPV reference. Will it work? Let's see. If E is negative, the first case scenario, right, where E is negative, if E is first case, if E is positive, that means I'm on the left hand side. If E is positive, it will compare with 0. The net thing would also come out to be positive. The PI has an integrator, so it will increase the output voltage, right? So VPV reference will increase. That means I will start moving from left hand side towards right hand side. On the other hand, if I'm on the right hand side, then my E is going to be negative. If E is negative, the input to the PI controller is going to be negative, and then my VPV reference will start reducing, and I will start moving towards left hand side, right? If you see, in fact, just the integral term is also good enough to explain the basic operation. You don't need essentially a proportional term. But you might want to use both and maybe other terms also along with this, right? So it could be other implementation also of this controller G of S. But in itself, this seems as a very basic implementation which uses the basic principle of incremental conductance, and but in a little bit different, the utilization is a little bit different. Instead of a digital algorithm, now you have implement this thing using a PI controller, which could be done either in analog or a digital controller. So this is one of the variation I was talking about. Let me show you one more variation. You see in this one there is everything seems okay. The only thing is the divider circuit, right, which might not be very popular circuits, and thus the other implementation actually talks about realizing or achieving the same without using these divider circuits. So let us have a look at the second version or the second flavor of the incremental conductance method, which is not exactly incremental conductance, which has a little bit difference. To talk about the method, let me take an example of a DC to DC boost converter, which is integrating the PV. Right, so here let's say we have a boost converter, and its output is let's say fed to a load. So how does if I draw the waveforms for this boost converter, this switch S closes for some duration and then remains off for some duration. If I draw the inductor current IL, let me assume it's a continuous conduction mode. So during the on switch on operation, the inductor current rises, and during off it falls. Right. What about the capacitor current? Let's say the current flowing inside the capacitor, if I want to draw. Right, so let's assume that the panel provides the average current, right, and therefore all the ripple flows through the capacitor, right. So yeah, this is going to be IC, which is equal to minus times the ripple component in the inductor current. Once I have drawn IC, I can further extend this and draw the capacitor voltage VC. Right, now VC voltage will have a very small ripple depending on how large the capacitance value that we are using. So whenever the current is positive in the capacitor, the voltage will rise, and whenever the current is negative, the voltage will fall. So the voltage is falling in this period, right, and then it is rising here, and it's rising here, right. This is roughly how the capacitor voltage would look like. Let me draw it on the right hand side now. If you see, if I only draw the capacitor voltage, right, which is, let's say, this kind of waveform, right, what it essentially says is, if I'm using a DC to DC converter along with the panel to feed to a load could be resistive, load could be a battery, right, load could be anything, then the PV terminals are going to have a very, very small value of ripple. If you use a very large C, this ripple magnitude is going to be very small, but nevertheless there is going to be ripple. If there's a ripple in PV panel, right, its current will also have a very small ripple. Why? Because if you see the panel, the current versus voltage characteristics is like this. So if the voltage increases, the current reduces, right? If I go from point A to point B, my voltage is increasing, current is reducing. And if I go from B to A, voltage reduces, current increases. So if you see, the panel current and voltage has a opposing or rather inverse relationship, and therefore if the panel voltage is increasing, And if I draw the panel current would actually be decreasing. So this is how the panel current would look like. Same thing, this ripple is going to be probably much smaller as compared to what I have shown here, but still there's going to be a very small ripple in both panel voltage as well as panel current. Alright, so this sort of establishes our system and its behavior. Now let us try to focus on the condition for maximum power. We draw P versus V graph. If you see on the left hand side, right, as V dot is positive, P dot is also positive, and therefore the multiplication of E dot and P dot is also going to be positive. On the right hand side, V dot is negative, it's falling. If I move from left to right, power is also falling, and again the multiplication is there going to be positive. And at this point you can see P dot, which is the slope of power, is going to be 0, and therefore this V dot P dot is going to be 0. Right? The same thing, this is the condition. Let me look at these graphs, the voltage versus time and the current versus time at different instants. For example, let me choose this instant t1. At t1, what is happening? Let me make a small table here. Let's say I'm talking about instant t1, right? So V dot is positive, right? Why? Because dV by dt is positive. I can see the slope is positive here. Di by dt is negative, right? So I dot is negative, and what about the power dot? Now the power dot here is now dependent on whether we are on the left hand side or right hand side. So if I'm on the if I'm on the left hand side, right, then power dot is positive, and if I'm on the right hand side, then the power dot is negative. Therefore at this instant t1, if I find V dot and if I find I dot, and if I use I dot and V dot, and if I multiply V dot into I dot, I'm going to get P dot, right? And further, if I multiply this V dot into P dot, right, and if I check the sign, if this is greater than 0, I am on the left hand side. If this is less than 0, I am on the right hand side, right? This is true for instant t1. Similarly, you can do same exercise for instance t2, right, where t2 is an instant in this graph where the voltage is, let's say, falling. So t2 voltage is falling, so V dot is negative, I dot is positive. If V dot is negative, right, if I am on the left hand side, right, if I am on the left hand side, and then V dot into P dot must be positive. If I am on the right hand side, then V dot into P dot must be negative, right? And thus again I can measure this V dot, I can measure I dot, I can multiply, get a P dot, further multiply with V dot, and then find what is the V dot P dot value, and based on that I can decide. So here if you see, the natural oscillations across the panel are being used to find whether we are operating on the left hand side or the right hand side of the graph. The only advantage you see is that there is a multiplication. In fact, there are two multiplications, but there is no division, right? So that in a way sort of helps in terms of the implementation. Let me show you the how we can implement this. So let's say I measure the voltage V, then I do d by dt, I get P dot, right? Similarly, I use this V, and I use the current I, then I multiply each other, then I get P, and I use another block d by dt, so that I get P dot, right? Once I get V dot P dot, then I can multiply these two, right, to get P dot into P dot. Now, as you understand, I can do anything. I can either do a analog digital controller where I can check if this is less than 0, increase voltage, greater than 0, decrease voltage, or I can do what I did in the previous technique, which is I can compare it with 0, pass it through an proportional or an integral or a proportional integral controller, and determine the reference voltage for PV. Thus, if V dot P dot is positive, right, if V dot P dot is positive, then you see that V reference PV will increase, right, which makes sense because you are on the left hand side. If V dot P dot is negative, then V reference P would be reduced, which makes sense because we'll be, in that case, we will be on the right hand side. So these are just two variations. At one point of time, the incremental conductance method and the MPP methods were one of the most one of the most explored research areas at one point in time. And if you look back and you see, there are so many other variations and so on proposed in the literature around that time.